Now in this lecture we'll answer two questions. The first question we find out the area of this triangle, the green triangle, triangle ABC. In the second question we find out the length of this line segment AP that equals to x. We have to find out the value of x. So we start with the first question. In the drawing we have quadrilateral ABPQ, and we know that AQ equals to AC. That is to say, triangle ACQ is an isosceles triangle. We also know that this is angle QPC that equals to 60 degrees inside. This is angle ABC that is also equals to 60 degrees inside. This is angle PQC that is a right angle. In addition, we know that side AB equals to 5 units in its length. This is line segment PC that is equals to 4 units in its length. Again, our task is to find out the area of this green triangle, triangle ABC. So first of all, we will do a construction. That is to say, from this point A, we draw perpendicular on the base QC. QC is the base of the isosceles triangle, triangle AQC. Triangle AQC is an isosceles triangle because side AQ equals to side AC, and QC is the base of this isosceles triangle, triangle AQC. So from point A, we draw perpendicular on the base QC. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We will define the touching point of the perpendicular from point A and the base QC. This point is point M. We have the rule. Here we can implement rule 22. I'll repeat quickly on rule 22. According to rule 22, the perpendicular to the base of an isosceles triangle bisects the base. So in the drawing we have triangle ABC. This is an isosceles triangle. This is an isosceles triangle because side AB equals to side AC. The base of this isosceles triangle, triangle ABC, is BC. And according to this rule, rule 22, the perpendicular to the base, here AM is the perpendicular to the base BC. The perpendicular AM bisects the base BC. That is to say, BM equals to MC. Okay, so we can implement rule 22 in our drawing. Why? Because in our drawing, this is the isosceles triangle, triangle QAC. QC is the base of the isosceles triangle, triangle QAC. According to rule 22, the perpendicular AM to the base QC bisects the base QC. That is to say, QM equals to MC. So if we define the length of line segment QM as A, then the length of line segment MC must be also equal to A because they are equal to each other according to rule 22. In the next step, we will extend the perpendicular AM by straight line until it touches line segment PC. And we will define the touching point of the extended perpendicular AM with side PC. This point is point N. AM is a perpendicular, it is absolutely a straight line. when you extend the straight line AN by straight line, the result AN must be also a straight line, because when you extend the straight line by straight line, the result must be a straight line. So AN is a straight line. If you focus on the right side of the straight line AN at point M, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 states that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the right side of the straight line AN at point M? We have this angle that is a right angle plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. So in the right big triangle, triangle PQC, 90 degrees plus 60 degrees is 150 degrees. Therefore, this third missing angle must be equal to 30 degrees in its size, according to the rule that states that the sum of the angles in any triangle is equal to 180 degrees. Therefore, this third missing angle must be equal to 30 degrees in its size. Likewise, in the small right triangle NMC, 90 degrees plus 30 degrees is 120 degrees. Therefore, this third missing angle must be equal to 60 degrees in its size according to the sum rule. It says that the sum of the angles in any triangle is equal to 180 degrees. Actually, it is very easy to see that the big right triangle PQC is similar to the small right triangle, triangle NMC, according to angle similarity rule. I will explain anyway why the big triangle PQC is similar to the small right triangle, triangle NMC. First of all, this angle C, that equals to 30 degrees in its size, is a common angle that belongs to both triangles. Angle C belongs to the big right triangle PQC, and angle C also belongs to the small right triangle, triangle CNM. So we can write down that angle C equals to itself as a common angle that belongs to both triangles. In addition, those two angles are both equal to 90 degrees and therefore they are equal to each other. And finally, those two angles are both equal to 60 degrees and therefore they are equal to each other. So we should find out that all the angles of the big right triangle PQC are correspondingly equal to all the angles of the small right triangle, triangle NMC. And therefore, those two right triangles are similar to each other according to angle similarity rules. So I write it down. So if we found out that the big right triangle PQC is similar, this is the sign of similar, to the small right triangle, triangle MNC, according to angle similarity rule. And from the fact that the big right triangle PQC is similar to the small right triangle, triangle NMC, we will derive that the following relationship exists between their sides. We will derive that side NC of the small right triangle, triangle NMC, over side PC of the big right triangle PQC is equal to side MC of the small right triangle NMC over side QC of the big right triangle, triangle PQC. Repeat again, from the fact that the big right triangle PQC is similar to the small right triangle, triangle NMC, we will derive that the following relationship exists between their sides. We will derive that side NC of the small right triangle MNC over side PC of the big right triangle PQC is equal to side MC of the small right triangle MNC over side QC of the big right triangle PQC. NC is the missing side, so we leave it as it is. Over PC. PC equals to 4 units in its length according to what is given as the question. And it is equal to MC. MC equals to A units in its length according to our definition. Over QC. QC equals to A plus A, that is 2A. So in total we found out that NC over 4 equals to A over 2A. Here we have A in the numerator and A in the denominator, so A will get cancelled. So on this side of the equation we left only with 1/2. So 1/2 equals to NC over 4. Here we will multiply this equation by 4 and we will get that NC equals to 4 over 2, that is 2. So if you found out that NC, the missing side NC, equals to 2 units in its length. This is the missing side NC, that equals to 2 units in its length. In the next step, I'll copy the big triangle A and B, and in your page we will analyze this big triangle, triangle A and B. Actually, this is the big triangle A and B that are copied from the original drawing. Side AB equals to 5 units in its length according to what is given as the question. Those triangles are both equal to 60 degrees. So in this triangle A and B, 60 degrees plus 60 degrees is 120 degrees, and therefore this third missing angle must be equal to 60 degrees in its size, according to the rule that states that the sum of the angles in any triangle is equal to 180 degrees. So this third missing angle must be equal to 60 degrees in its side, and therefore triangle A and B is an equilateral triangle because of the fact that all of its angles are equal to each other. So triangle A and B is an equilateral triangle. We know that all the sides of any equilateral triangle are equal to each other. AB equals to 5, therefore AN must be also equal to 5. And B also must be equal to 5 units in its length. So actually, this is side NB that equals to 5 units in its length. What is the length of the missing side? Side CB. From the drawing, it is very easy to see that CB equals to NB minus NC. Again, NB minus NC equals to CB. So I write it down. CB equals to NB minus NC. So CB equals to NB, NB equals to 5 units in its length, minus NC, NC equals to 2 units in its length, so in total CB equals to 5 minus 2, that is 3. So if you found out that CB equals to 3 units in its length, this is the length inside CB, that is equals to 3 units in its length. In the next step, we will do another construction, that is to say from point A, we will go perpendicular on CB. Again, from point A, we will go perpendicular on CB. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point A and CB. This point is point O. In the next step, I'm copying, before that, we define the length of side AO as H. So in the next step, I'll copy the right triangle AOB in a new page, and we find out the length of side AO that is equals to H. So actually, this is the right triangle AOB that is copied from the original drawing. In this right triangle AOB, sin of 60 degrees equals to AO over OB. So I write it down. Sinus 60 degrees equals to AO over AB. AO equals to H according to our definition, AB equals to 5 units in its length. So in total, we found out that sinus 60 degrees equals to H over 5. We know that sinus 60 degrees equals to the square root of 3 over 2. So square root of 3 over 2 equals to H over 5. Here we will multiply this equation by 5. And finally we get that H equals to 5 times square root of 3 over 2 units in its length. Limits inside AO that is equal to H is equal to 5 times square root of 3 over 2 units in its length. Our task is to find out the area of this green triangle, triangle ABC. So what is the area of the green triangle, triangle ABC? The area of this green triangle ABC equals to the base CB times the height H over 2. write it down. There are the triangle ABC. It is equals to the base of the triangle, that is CB, times the height edge over 2. We already found out that the base CB equals to 3 units in its length times edge. We just found out that edge equals to 5 times square root of 3 over 2. And you have to divide it by 2. So in the numerator of this expression we have 5 times 3, that is 15, times square root of 3 over 2 times 2, that is 4. So we found out that the area of this triangle ABC, it is equals to either 15 times square root of 3 over 4 square units in its size, or in terms of numbers, is equal to 6.5 square units in its size. Repeat again, if we found out that the area of this green triangle ABC is equals to either 15 times square root of 3 over 4 square units in its size, or in terms of numbers, the area of this triangle ABC is equals to 6.5 square units in its size. So we finish with the first question. In the next step, I will present to you the second question, and we will answer on the second question of this lecture. In the second question, our task is to find out the length of this short line segment AP that is equals to x. We have to find out the value of x. So in the drawing we have a semicircle. This is point O, that is the center of this semicircle. You know that this is line segment PO, that is equals to 10 units in its length. This is line segment QP, that is equals to 21 units in its length. This is chord QS, that is equals to 16 units in its length. This is angle PQC, that is a right angle. Again, our task is to find out the length of this short line segment AP, that is equals to x. We have to find out the value of x. So first of all, we will complete this semicircle to a circle. So completed the semicircle to a circle, and we will extend line segment QP by a straight line until it touches the circle. We define the touching point of the extended line segment QP with this circle. This point is point M. In the next step, we will join points S and M together by a straight line. So by doing all those constructions, we get the peripheral angle SQM. This is peripheral angle SQM. That is equals to 90 degrees in its size. And peripheral angle SQM subtend on chord SM. Again, peripheral angle SQM, that is the right angle, subtend on chord SM. So here we can implement rule 5. Repeat quickly rule 5. According to rule 5, any peripheral angle that is equal to 90 degrees must subtend on the diameter of the circle. In the drawing you have a circle. This is peripheral angle MAN, that is the right angle. That is to say it is equal to 90 degrees in its size. So peripheral angle MAN, that is the right angle, must subtend on the diameter of the circle. And indeed, peripheral angle MAN subtend on MA or on chord MN, that is the diameter of this circle. So according to this rule 5, any peripheral angle that is equal to 90 degrees in its size must subtend on the diameter of the circle. So we can implement rule 5 in our drawing. Why? Because in our drawing, this is peripheral angle SQM, that is equal to 90 degrees in its size, and therefore, according to rule 5, peripheral angle SQM must subtend on the diameter of this circle. Peripheral angle SQM subtend on chord SM, and therefore, according to rule 5, SM must be the diameter of this circle. So, right now, if you found out that chord SM is the diameter of this circle according to rule 5. We define the radius of this circle as R. Point O is the center of this circle. Point S is the point of the circle itself. Therefore, OS is the radius of this circle. That is equals to R according to our definition. Likewise, OM is also the radius of this circle. Therefore, it is equal to R according to our definition. In the next step, we do a construction, that is to say, from point O, that is the center of this circle, we will draw perpendicular on QP. Again, from point O, we will draw perpendicular on QP. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and QP. This point is point N. If we focus on the right big triangle SQM, this is angle QMS. We define this angle QMS as alpha. Angle alpha, it is a common angle that belongs to both triangles. Angle alpha belongs to the big right triangle QMS, and angle alpha belongs to the small right triangle NOM. Okay, so if we focus on the big right triangle QMS, this is angle alpha. This angle equals to 90 degrees in its size, and therefore this third missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. Likewise, in the small right triangle NOM, this angle equals to alpha, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha. Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. Actually, it is very easy to say that the big right triangle SQM is similar to the small right triangle ONM according to angle similarity rule. So I'll explain anyway why the big triangle SQM is similar to the small right triangle ONM. First of all, this is angle alpha, that is a common angle that belongs to both triangles. So we can write down that angle alpha equals to itself as a common angle that belongs to both triangles. In addition, those two angles are both equal to 90 degrees and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So if you found out that all the triangles of the big right triangle SQM are correspondingly equal to all the triangles of the small right triangle ONM. And therefore, those two right triangles are similar to each other according to angle similarity rule. So I write it down. You actually found out that the big right triangle SQM is similar, this is the sign of similar, to the small right triangle ONM. According to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side NO of the small right triangle ONM over side QS of the big right triangle SQM is equal to side OM of the small right triangle ONM over side SM of the big right triangle QSM. Repeat again, from the fact that the big right triangle SQM is similar to the small right triangle ONM, we derive that the following relationship exists between their sides. We will derive that side ON of the small right triangle ONM over side QS of the big right triangle SQM is equal to side OM of the small right triangle ONM over side SM of the big right triangle SQM. ON is the missing side, so we leave it as it is. Over QS. QS equals to 16 units length according to what is given as the question. And it is equals to OM. OM is the radius of the circle that is equals to R. Over SM. SM is the diameter of the circle that is equals to R. So in total we found out that ON over 16 equals to R over 2R. So we have R in the numerator and R in the denominator, so R will get cancelled. If we cancel R, in this side of the question we left only with 1/2 equals to ON over 16, or ON over 16 equals to 1/2. Here we multiply this equation by 16 and we get that the missing side ON equals to 16 over 2, that is 8. So if you found out that this is the missing side, this is the missing side ON, that is equals to 8 units in its length. In the next step, we will do a construction that is to say, from the center of this circle, that is actually point O. Actually, the next step, we will implement the Pythagoras theorem on this right small triangle ONP. Again, we will implement the Pythagoras theorem on this small right triangle ONP. So I'll copy the small right triangle ONP in a new page, and we will implement on it the Pythagoras theorem. Here by PT is the progression from Pythagoras theorem. Okay, this is the small right triangle P and O that are coming from the original drawing. This small right triangle, actually according to the Pythagoras theorem, in a right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. This right triangle P and O, PO squared, that is the square of the hypotenuse, is equal to Pn squared plus On squared. PO is 10, therefore PO squared is 10 squared, that is 100. And it is equals to Pn squared. Pn is the missing side, so we leave it as it is. It is Pn squared plus On squared. On is 8, therefore On squared is 8 squared, that is 64. So in total, we should find out that 100 equals to Pn squared plus 64. Here we will subtract 64 from this equation, and we get that Pn squared equals to 100 minus 64, that is 36. Pn squared equals to 36. Here we will take a root out of this equation, and finally get that Pn equals to the square root of 36, that is 6. So I should find out that the missing side Pn equals to 6 units in its length. This is the missing side Pn that equals to 6 units in its length. What is the length of this missing 97 Qn? From the drawing, it is very easy to see that Qn equals to Qp minus Np. Again, Qp minus Np equals to Qn. So I write it down. We actually found out that Qn equals to Qp minus Np. So Qn equals to Qp. Qp equals to 21 units in its length, according to what is given in the question, minus Np. We just write down found out that Np equals to 6 units in its length. So Qn in total equals to 21 minus 6, that is 15. So if you found out that Qn, the missing side Qn equals to 15 units in its length. So okay, this is the missing side Qn is equals to 15 units in its length. In the next step, we join points O and Q together by a straight line. Point O is the center of this circle, point Q is the point of the circle itself, therefore OQ is the radius of this circle, that equals to R according to our definition. In the next step, I'll copy the right triangle Q and O in a new page, and we will implement the Pythagoras theorem on this right triangle, triangle Q and O. We'll implement the Pythagoras theorem on this right triangle, triangle Q and O. Qn equals to 15 units in its length. On equals to 8 units in its length. And the hypotenuse OQ is the radius of this circle that equals to R. Here by PT is the proportion for Pythagoras theorem. So actually this is the right hand triangle, triangle Q and O that according from the original drawing. This right triangle Q and O, according to the Pythagoras theorem, QO squared, that is the square of the hypotenuse, equals to QN squared plus NO squared. So I write it down. QO squared, that is the square of the hypotenuse, equals to QN squared plus NO squared. The hypotenuse QO equals to R, therefore QO squared equals to R squared. And it is equals to QN squared. QN is 15, therefore QN squared is 15 squared, that is 225. Plus NO squared. NO is 8, therefore NO squared is 8 squared, that is 64. So in total, I found out that R squared equals to 225 plus 64, that is 289. So R squared equals to 289. Here we'll take a root out of this equation, and finally get that R equals to the square root of 289, that is 17. So if we found out that the radius R of this circle is equal to 17 units. We know that OA is also the radius of this circle, that equals to R. OA is also the radius of the circle, that equals to R, and R equals to 17. But OA also equals to AP plus PO. OA equals to AP plus PO. So write it down. OA equals to AP plus PO. AP is the line segment that we are looking for in this question. It is equal to X plus PO. According to what is given in the question, PO equals to 10 units in its length. In total, if you found out that 17 equals to R equals to OA equals to AP plus PO equals to X plus 10. From this long equation, we will derive that X plus 10 equals to 17, or 17 equals to X plus 10. 17 equals to X plus 10. Here we will subtract 10 from this equation, and we get that 17 minus 10 is 7 equals to X. So if you found out that the last segment that we're looking for this question, AP is equals to X, AP is equals to X is equal to 7 units in its length. So the answer to the question is that the length of the short line segment AP is equals to X is equal to 7 units. That is the answer to the question. So we finish with the second question. In the next step, I'll summarize the lecture. We'll start with the first question, of course. Our task in the first question is to find out the area of this green triangle, triangle ABC. So in the drawing, we have the big quadrilateral QABCP. It is given as a question that AQ equals to AC. Therefore, triangle QAC is an associated triangle, and the base of the associated triangle QAC is QC. It is also given us the question that this angle QPC equals to 60 units in its size. This is angle PQC, this is a right angle. This is line segment PUC, that equals to 4 units in its length. This is angle ABC, that is also equals to 60 degrees. This is angle ABC, that is also equals to 60 degrees in its size. And finally, this is side AB, that is equals to 5 units in its length. Again, our task is to find out the area of this grand triangle, triangle ABC. So first of all, we actually did a construction. That is to say, from point A, we go perpendicular on the base QC of the associated triangle, triangle AQC. Again, from point A, we go perpendicular on the base QC of the associated triangle, triangle AQC. So here we can implement rule 22. According to rule 22, the perpendicular to the base of an associated triangle bisect the base. Okay, again, according to rule 22, the perpendicular to the base of an associated triangle bisect the base. So in our drawing, the perpendicular AM to the base QC of the associated triangle, triangle QAC bisect the base QC. That is to say, it divides the base QC into two halves. The first half is QM, the second half is MC, and of course they are equal to each other. That is to say, QM equals to MC. So we define the length of QM as A, then the length of MC must be also equal to A because they are equal to each other according to rule 22. In the next step, we extended the perpendicular AM by a straight line until it touches side PC at this point. We define the touching point of the extended perpendicular AM with side PC, this point is point N. AM is a perpendicular, it is absolutely a straight line. When we extended the straight line AM by straight line, the result is AN. When we extend the straight line by straight line, the result must be a straight line. Therefore, AN is also a straight line. So if you focus on the right side of the straight line AN at point M, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 states that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have on the right side of the straight line AN at point M? We have this angle that is right angle plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. We'll focus on the big right triangle, triangle PQC. On the big right triangle PQC, 90 degrees plus 60 degrees is 150 degrees. And therefore, this third missing angle must be equal to 30 degrees in its size. According to the rule, then the sum of the angles in any triangle is equal to 180 degrees. Likewise, in the small right triangle NMC, 90 degrees plus 30 degrees is 120 degrees. And therefore, this third missing angle must be equal to 60 degrees in its size according to the sum rule that says that the sum of the angles in any triangle is equal to 180 degrees. It is very easy to see that the big right triangle PQC is similar to the small right triangle NMC according to angle similarity rule. I will prove it anyway. Find the big right triangle PQC similar to the small right triangle NMC. First of all, this angle C that equals to 30 degrees in size. It is a common angle that belongs to both triangles. In addition, those two angles are both equal to 90 degrees and therefore they are equal to each other. And finally, those two angles are both equal to 60 degrees and therefore they are equal to each other. So if we prove that all the figures of the big right triangle PQC are correspondingly equal to all the figures of the small right triangle NMC, and therefore those two right triangles are similar to each other according to angle similarity rule. I'll repeat again. If you found out that the big right triangle PQC is similar, this is the sign of similar, to the small right triangle NMC according to angle similarity rule. And from the fact that the big right triangle PQC is similar to the small right triangle NMC, we will derive that the following relationship exists between their sides. We will derive that side MN, we will derive that side NC of the small right triangle NMC over side PC of the big right triangle PQC is equal to side MC of the small right triangle NMC over side QC of the big right triangle PQC. So if again we derive that side NC of the small right triangle NMC over side PC of the big right triangle PQC is equal to side MC of the small right triangle MNC over side QC of the big right triangle PQC. NC is the missing side, so we leave it as it is, over PC. PC equals to 4 units in its length according to what is given as the question. And it is equals to MC. MC equals to A according to our definition over QC. QC equals to A plus A, that is 2A. So in total we found out that NC over 4 equals to A over 2A. We have A in the numerator and A in the denominator, so A will get cancelled, and inside of the equation we have to only with 1/2 equals to NC over 4, or NC over 4 equals to 1/2. Here we multiply this equation by 4 and finally found out that NC, the missing side NC equals to 4 over 2, that is 2. This is the missing side NC, that equals to 2 units in its length. In the next step I copy the big right triangle NAB in a new page and analyze this big triangle NAB. This is the big triangle NAB that is going to the original drawing. Those two angles are both equal to 60 degrees. AB equals to 5 units in its length according to what is given as the question. So in this triangle A and B, 60 degrees plus 60 degrees is 120 degrees. And therefore this first missing angle must be equal to 60 degrees in its size according to the rule that the sum of the angles in any triangle is equal to 180 degrees. So we actually found out that triangle A and B is an equilateral triangle. Why? Because all of its angles are equal to each other. We know that all the sides of any equilateral triangle are equal to each other. AB equals to 5, therefore AN must be also equal to 5, and B must be also equal to 5. So actually, this is side NB of the equilateral triangle ANB, that is equals to 5 units in its length. And B equals to 5 units in its length. What is the length of this missing side CB? From the drawing it is very easy to see that CB equals to NB minus NC. Again, NB minus NC equals to CB. CB equals to NB minus NC. So CB equals to NB, that is 5, minus NC, that is 2. So in total, CB equals to 5 minus 2, that is 3. This is the missing side CB, that equals to 3 units in its length. In the next step, we did another construction, that is to say, from point A, we go perpendicular on CB. Again, from point A, we go perpendicular on CB. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point A and CB. This point is point O. We define the length of AO as H. In the next step, I copy the right triangle AOB in a new page, and we found out the length of AO that is equal to H. So actually, This is the green right triangle AOB that is going from the original drawing. In this triangle, right triangle AOB, sine of 60 degrees equals to AO over AB. Sine of 60 degrees equals to AO over AB. AO is edge, according to our definition, over AB. The hypotenuse AB is 5. So in total, we can find out that sine of 60 degrees equals to edge over 5. Sine of 60 degrees equals to square root of 3 over 2. So square root of 3 over 2 equals to edge over 5. Here we multiply this equation by 5 and finally found out that edge equals to 5 times square root of 3 over 2. This is the inside edge that equals to 5 times square root of 3 over 2 units in its length. Edge equals to 5 times square root of 3. Edge equals to 5 times square root of 3 over 2 units in its length. Our task is to find out the area of this green triangle, triangle ABC. So the area of this green triangle must be equal to the base CB times the height edge over 2. Again, the area of the green triangle ABC must be equal to the base CB times the height edge over 2. CB is 3 times edge. Edge is 5 times square root of 3 over 2. And we have to divide it by 2 again. In the numerator we have 3 times 5, that is 15, times square root of 3. In the numerator we have 2 times 2, that is 4. So in total we found out that the area of this green triangle, triangle ABC, is equals to either 15 times square root of 3 over 4 square units in its size, or in terms of numbers, the area of this green triangle ABC is equal to 6.5 square units in its size. So we finish with the first question. In the next step I presented to you the second question and we solve the second question of this lecture. In the second question, our task is to find out the length of this short line segment AP that is equals to x. We have to find out the value of x. So in the drawing we have a semicircle. Point O is the center of this semicircle. This is line segment PO that is equals to 10 units in its length. This is line segment QP that is equals to 21 units in its length. This is called QS that is equals to 16 units in its length. This is angle PQC that is right angle. Again, our task is to find out the length of this short line segment AP that is equals to x. We have to find out the value of x. So in the first step, we completed the semicircle to a circle, and we extended line segment QP by a third line until it touches the circle. We define the touching point of the extended line segment QP with this circle. This point is point M. In the next step, we join points M and S together by a straight line. By doing all those constructions, we can do peripheral angle SQM. This is peripheral angle SQM, that is a right angle. Peripheral angle SQM subtend on chord SM. Again, peripheral angle SQM subtend on chord SM. We can implement here rule 5. According to rule 5, any peripheral angle that is equal to 90 degrees in size must subtend on the diameter of the circle. This is peripheral angle SQM that is equal to 90 degrees in size. And therefore, this peripheral angle SQM must subtend on the diameter of the circle. Peripheral angle SQM subtend on chord SM, and therefore, according to rule 5, SM must be the diameter of the circle. SM is the diameter of the circle according to rule 5. In the next step, so point O is the center of the circle, point S is the point of the circle itself, therefore OS is the radius of this circle. We define the radius of this circle as R, therefore OS equals to R. Likewise, OM is also the radius of this circle, that is equal to R according to our definition. In the next step, we did the construction, that is to say from the center of this circle, that is to say from point O, we do perpendicular on QP. Again, from point O, we do perpendicular on QP. So here this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and QP. This point is point N. So if we focus on the big right triangle SQM, this is the big right triangle SQM, we define this angle as alpha. Angle alpha is the common angle that belongs to both triangles. Angle alpha belongs to the big right triangle SQM, and angle alpha also belongs to the small right triangle, triangle ONM. So angle alpha is the common angle that belongs to both triangles. In the big right triangle SQM, this angle is alpha. This angle is 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. Likewise, in the small right triangle ONM, this is angle alpha. This angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. It's very easy to see that the big right triangle SQM is similar to the small right triangle ONM according to angle similarity rule. So I'll prove anyway why the big triangle SQM, the big right triangle SQM is similar to the small right triangle, triangle ONM. First of all, this is angle alpha, that is a common angle that belongs to both triangles, so can I know that angle alpha equals to itself is a common angle that belongs to both triangles. In addition, those two angles are both equal to 90 degrees, and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So if you found out that all the figures of the big right triangle SQM are correspondingly equal to all the figures of the small right triangle, triangle ONM. And therefore the big right triangle SQM is similar to the small right triangle ONM according to angle similarity rule. So if you found out that the big right triangle SQM is similar, this is the sign of similar to the small right triangle OMN according to angle similarity rule. And from the fact that the big right triangle SQM is similar to the small right triangle ONM, we will derive that the following relationship exists between their sides. We will derive that side ON of the small right triangle ONM over side SQ of the big right triangle SQM is equal to side OM of the small right triangle ONM over side SM of the big right triangle, triangle SQM. Because again, we derive that side ON of the small right triangle ONM over side QS of the big right triangle SQM is equal to side OM of the small right triangle ONM over side SM of the big right triangle, triangle SQM. ON is the missing side, so we leave it as it is. Over QS. QS equals to 16 units in itself according to what is given in the question. And it is equals to OM. OM is the radius of the circle that is equals to R over SM. SM is the diameter of the circle that is equals to 2R. So in total, if you found out that ON over 16 equals to R over 2R. We have R in the numerator and R in the denominator, so R will get cancelled. So in this side of the equation, we left only with 1 half equals to ON over 16, or ON over 16 equals to 1 half. Here we multiply this equation by 16 and found out that the missing side ON equals to 16 over 2, that is 8. This is the missing side ON that is equal to 8 units in its length. In the next step, we implemented the Pythagoras theorem on this small right triangle, triangle ONP. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So here this is the small right triangle ONP that I copied from the original drawing. This small right triangle ONP, or P squared, that is the square of the hypotenuse, equals to NP squared plus NO squared. OP or PO equals to 10, therefore PO squared is 10 squared, that is 100. And it is equals to Pn square. Pn is the missing side, so we leave it as it is, so it is Pn square plus On square. On is 8, therefore On square is 8 square, that is 64. So in total, we should found out that 100 equals to Pn square plus 64. Here we subtract the 64 for this equation, and we found out that Pn square equals to 100 minus 64 is 36. So Pn square equals to 36. Here we took out of this equation. And finally found out that Pn equals to the square root of 36, that is 6. So here, this is the missing side NP, that is equal to 6 units in its length. What is the length of the missing line segment QN? From the drawing, it is very easy to say that QN in total equals to QP minus NP. Again, QP minus NP equals to QN. Q1 equals to QP minus NP. So Q1 equals to QP, QP equals to 21 minus NP. NP equals to 6 units in its length. So in total, Qn equals to 21 minus 6, that is 15. So Qn equals to 15 units in its length. The next step, we join points O and Q together by straight line. Point O is the center of the circle, point Q is the point of the circle itself, therefore OQ is the radius of this circle, that is equals to R. In the next step, we'll copy again right triangle Q and O in the equation and implemented the Pythagoras theorem in this right triangle Q and O. This is again right triangle Q and O that are going from the original domain. According to the Pythagoras theorem, this right triangle Q and O, QO squared, that is the square of the hypotenuse, equals to QN squared plus ON squared. QO is R, therefore QO squared is R squared, and it is equals to QN squared. QN is 15, therefore QN squared is 15 squared, that is 225. Plus NO squared. NO is 8, therefore NO squared is 8 squared, that is 64. So in total, we found out that R squared equals to 225 plus 64. 225 plus 64 is 289. So if you found out that R squared equals to 289, here we took out of this equation and found out R, the radius of the circle, equals to the square root of 289, that is 17. So if you found out that the radius R of this circle is equal to 17 units in its length. We also know that OA is also the radius of this circle. So here, the radius of the circle is the radius of the circle R equals to 17 units, and OA is also the radius of the circle. But OA, the radius OA also equals to AP plus PO. So you can write there that OA equals to AP plus PO. AP equals to X, that is the line segment that we are looking for in this equation, and PO equals to 10. Again, AP equals to X and PO equals to 10. From this long equation, we derive that 17 equals to X plus 10. 17 equals to X plus 10. Here we subtract 10 from this equation, and finally found out that X equals to 17 minus 10, that is 7. X equals to 7. X is actually AP. AP equals to X, and X equals to 7 units in its length. Again, AP equals to X, and X equals to 7 units in its length. AP equals to X, and X equals to 7 units in its length. So the answer to the question is that the length of this line segment AP is equals to X is equal to 7 units. Okay, thank you very much.